Logarithmic function. Consider the function f of x equals 2 to the x power. If x is 0, then I have 2 to the 0 power. If my x is 1, I have 2 to the first power. If x is 2, I have 2 to the second power. If x is 3, I have 2 to the third power. If x is 4, I have 2 to the fourth power. So each value of x ends up being in the exponent of my function. If I were to find the inverse of that function, then my x would be the answer for 2 to the 0, and my output would be 0. My x would be 2 to the first power, which is 2, and my output would be 1. My input would be 2 to the second power, which is 4, and my output would be 2. My input would be 2 to the third power, or 8, and my output would be 3. My input would be 2 to the fourth power, which is 16, and my output would be 4. So the inverse function takes the answer and asks what was the exponent to start with. That is what a logarithmic function does. Definition of a logarithm. For b greater than 0, b does not equal 1, and a is greater than 0, the logarithm log base b of a is the number k such that b to the k equals a. In words, log base b of a is the exponent on the base b that gives a. We call b the base of the logarithm. For example, log base 5 of 25 equals 2, since 5 squared equals 25. The logarithm 2 is the exponent on the base 5 that gives 25. A logarithm is an exponent. In this example, find the logarithm. Part A, log base 2 of 32. 2 is our base. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 2 to the fifth power is 32. That means log base 2 of 32 equals 5, since 5 is the exponent. Part B, log base 4 of 64. 4 times 4 is 16, times 4 is 64. That gives us 3 4s, so our exponent is 3. Log base 4 of 64 equals 3. For part C, log base 9 of 81. 9 times 9 is 81, so that's 2 9s, which gives us 2. Log base 9 of 81 equals 2. Common logarithm. A common logarithm is a logarithm with base 10. We write log of a to represent log base 10 of a. For example, log of 100,000 means log base 10 of 100,000. We can use the log key on the calculator to find base 10 logarithms. It's important to keep in mind that a logarithm is an exponent. In this example, find the logarithm, part A, log of 10,000. Since we are using base 10, 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000. So we're looking at 10 to the fourth power. Another way that we can determine the exponent is by counting the zeros. 4. So log of 10,000 equals 4. In part B, we have log base 4 of 1/16. Remember that 4 to the negative 1 power is the same as 1/4. And 1 over 16 is the same as 1 over 4 squared, which means we have 4 to the negative 2 power. So our exponent is negative 2. Log base 4 of 1 over 16 equals negative 2. Part C, log base 3 of the square root of 3. The square root of 3 is the same as 3 to the 1/2 power. So we want to know what exponent would we need for base 3 to get the square root of 3. It's going to be the 1/2 power. Log base 3 of the square root of 3 equals 1/2. Properties of logarithm. For b greater than 0 and b not equal to 1, log base b of b is equal to 1. If your base and your answer are the same, the exponent has to be 1. Log base b of 1 equals 0. Anything to the 0 power is 1. Definition of logarithmic function. A logarithmic function base b is a function that can be put into the form f of x equals log base b of x, where b is greater than 0 and b does not equal 1. In general, the domain of a logarithmic function, log base b, is the set of all positive real numbers. In this example, we want to find the logarithm for part A, log base 5 of 5. Since our base and our answer are the same, our exponent has to be 1. Log base 5 of 5 equals 1. Part B, log base 5 of 1. In order for me to get a 1, 5 would have to be to the 0 power. So log base 5 of 1 equals 0. C, log base 3 of 0. We want to know 3 to what power is going to give us 0. Well, we know that 3 to the first is 3, 3 to the second is 9, 3 to the third is 27, so that's getting further from 0. 3 to the 0 is 1, 3 to the negative 1 is 1/3, 3 to the negative 2 is 1/9, 3 to the negative 3 is 1/27. So as you can see, our fractions are getting smaller, but we're not going to get to 0. Therefore, this has no solution. Part D, log base 3 of negative 9. We want our answer to be negative 9. We know that 3 squared is 9, and negative 3 squared is 9. We're not going to be able to get negative 9 with an even exponent, so this is no solution as well. It's important to keep in mind that, in general, the domain of a logarithmic function is the set of all positive real numbers. Properties of a logarithm. Logarithmic and exponential functions are inverses of each other. For an exponential function, f of x equals b of x, the inverse of x is equal to log base b of x. For a logarithmic function, g of x equals log base b of x, the inverse of g of x is b to the x power. In words, g of x equals log base b of x and f of x equals b to the x are inverse functions of each other. Composing logarithmic and exponential functions with the same base. For b greater than 0 and b not equal to 1, log base b of b to the x power is x. Base b with an exponent of log base b of x is just x, where x is greater than 0. In this example, find the logarithm. Part A, we have log base 4 of 4 to the third power. Because my base and the base of my answer are the same, it equals the exponent 3. Log base 4 of 4 to the third power equals 3. Part B, 3 to the exponent of log base 3 of 9. Because this base and this base are equal, I know that my answer is 9. 3 to the log base 3 of 9 power equals 9. Using logarithms to model authentic situations. The energy released by an earthquake is sometimes measured on the Richter scale. The Richter number R of an earthquake is given by R equals log of A divided by A sub 0, where A is the amplitude, your maximum value, of a seismic wave, and A sub 0, called the reference amplitude, is the amplitude of the smallest seismic wave that a seismograph can detect. In this example, in 2004, an earthquake in the Indian Ocean had an amplitude 1.6 times 10 to the 9th times the reference amplitude A sub 0. In 1985, an earthquake in Mexico City had an amplitude 6.3 times 10 to the 7th times A sub 0. We want to find the Richter number of the Indian Ocean earthquake. So looking at the Indian Ocean earthquake, our amplitude was 1.6 times 10 to the 9th times the reference amplitude A sub 0. What that means is A is going to equal 1.6 times 10 to the ninth times a sub 0. From our formula, we know R equals log of A divided by A sub 0. And from our word problem, we know that for the Indian Ocean, A equals 1.6 times 10 to the ninth A sub 0. So I can substitute into my equation R equals log of A, which is 1.6 times 10 to the ninth times A sub 0, divided by A sub 0. Solving, our A sub 0's cancel each other out. So that leaves us with log base 10 of 1.6 times 10 to the ninth. And that's something that we can easily calculate. So we have log 1.6. For scientific notation, we need EE. It's above our comma, second, comma, and then you just type your exponent, 9. Enter, and I get 9.204119983. We'll round to the tenths place, so R equals 9.2. So the Richter number of the Indian Ocean earthquake is 9.2. Part B, find the Richter number of the Mexico City earthquake. For Mexico City, our amplitude is 6.3 times 10 to the 7th times A sub 0. So what that tells us is our amplitude is 6.3 times 10 to the 7th times A sub 0. So we're looking for R again, and in this case we know that A is equal to 6.3 times 10 to the 7th times A sub 0. R equals log of A, which is 6.3 times 10 to the 7th A sub 0, divided by A sub 0. Again, our A sub 0's cancel, leaving me with log base 10 of 6.3 times 10 to the 7th. Calculating, we type log 6.3 E 7, enter, and we get 7.799340549, which rounds to 7.8. R equals 7.8. So the Richter number for the Mexico earthquake is 7.8. Part C. Find the ratio of the amplitudes of the Indian Ocean and Mexico City earthquakes. Anytime you find a ratio, you're dividing. Since the ratio is Indian Ocean first, then the Mexico City earthquake, our setup is 9.2, since that's the R for the Indian Ocean, divided by 7.8, since that's the R for the Mexico City earthquakes. 9.2 divided by 7.8 is 1.179. Rounding to the nearest tenth, 1.2. A logarithmic function is f of x equals log base b of a. Your definition of a logarithm, if I have log base b of a equals k, that's the inverse of b to the k equals a. Your common logarithm is your log of base 10. For your properties of logarithms, if I have log base b of b, that will always equal 1. If I have log base b of 1, that will always equal 0. Using logarithms to model authentic situations. One of the most common authentic situations is the Richter scale. We can use logarithms to find the magnitude of earthquakes and compare them to earthquakes in other areas.